Sometimes we can get a pretty deep understanding by looking at one simple problem and connecting it with a few other key concepts. The integral of Ws ds is one of such very interesting integrals in stochastic calculus. It's pretty simple by itself, but understanding it can help us grasp some key concepts in stochastic integral. One can also go really deep into the fundamental theoretical aspect of it. But here, I'll try to stick to its connections with some critical stochastic properties from a less abstract perspective. To begin with, it's not unintuitive to see that this integral is a random variable itself. And since Ws, the Brownian motion, is symmetric with respect to 0 and follows normal distribution, this integral must follow a normal distribution with mean 0 and some variance. I'll write down the variance first, and we'll show later how we can derive it, which is 1/3 t cubed. We'll look at three ways to understand this integral. First, with the understanding that it's a random variable, we can try to calculate its mean and variance directly. As we mentioned above, since Ws follows normal distribution with mean 0, its expected value should be just 0. Of course, you can use the properties of the mean of integrals or use properties of limits to calculate it in a pretty straightforward way. With the mean known, we can write down the variance using the definition directly, which will become a double integral. To solve this double integral, we need to use the expected value of Ws, which is minimum of Us. This is one of the Markov properties of Brownian motion. The rest is simple algebra, and I will leave it as exercise. Second, we can use the chain rule of derivatives or effectively integral by parts. Taking the derivative of Ws times s, integrate both sides, rearrange the terms. We get the desired integral as Wt times t minus integral of s dws. Note Wt times t can also be written as t times integral dws. So the integral is equivalent to integral of t minus s times dws. Now this hopefully looks more familiar to you as it's an Ito integral, and we can apply Ito isometry to solve it. The rest, I'll leave it as exercise. Finally, this integral is related to another integral, w squared dw. We can see this as ds, the first order in time, can be written as dws squared, the second order in dws. So it's not hard to see the two integrals are the first and the second order derivative of 1/3 ws cubed. Now integrate both sides, we see the two integrals sum up to 1/3 Wt cubed. We can write down the integral we were interested in as 1/3 Wt cubed minus this new integral, which is an Ito integral with mean 0, and its variance can be calculated via Ito isometry. We can also rearrange it to understand this new integral, of course, since we know it from the first two ways of understanding above already. Again, one can go really deep into the fundamental theoretical aspect of every single line I wrote down above, but hopefully these 3 points can already help you appreciate some of the important concepts of stochastic integral. Okay, thanks for watching and hope to see you next time.